afternoon. So we were left with an exercise here in trees. Show that the tree with exactly two vertices of degree 1 is a path. Has anybody tried to solve this? Has anybody solved this? Okay, so you try and then solve it next time. All right? And what about other exercises? I think that was the only one, apart from the one on the center, which is, as I said, too long to solve here in class. And you can solve it after class if you want. Okay? So please have a look at this. This is a simple one. Okay? So we were here. In this chapter, we have two types of problems which are rather similar to each other. That is the one of Euler tools, meaning you have a graph and you want to start from one vertex, go along all the graph by crossing each edge exactly once and come back to the original vertex. That's an Euler tool. Or start from one vertex, go through all the edges exactly one time, and then end in another vertex. That's an Euler trail. Okay? And the characterization of graphs where you can have such a thing is extremely easy. You can have an Euler tool, so the graph is called Eulerian, if and only if all vertices have even degree, and you have an Euler trail if you have at most two vertices of odd degree and all the others have even degree. Okay? That's for a connected graph, of course. A similar problem can be stated for vertices, and it's the problem of Hamilton cycles, Hamilton paths, which says, can you start from one vertex and come back to that vertex by touching all vertices, all other vertices just once? And if it's possible, then this is called an Euler Hamilton cycle, and the graph is called Hamiltonian. Also, there is the possibility, instead of starting from one vertex and in another vertex, and in between pass through all vertices exactly once, and that's a Hamilton path. Okay? While we have a very simple characterization of Eulerian graphs, we do not yet have a good characterization, so an if and only if condition for a graph to be Hamiltonian. Okay, we have seen a couple of one-way implications. Let me go back to them. If G is Hamiltonian, then this happens, that for every unempty proper subset S of vertices, if you take away the number, if you take away from G those vertices and the incident edges, then the number of components of the resulting graph is less than or equal to the number of elements in S itself. Okay? And this, as I said, can be used above all through the counter positive. That is, if you find a certain subset of vertices S such that the number of elements of S is strictly less than the number of components which you obtain by taking those vertices away, then you can be totally sure that the graph is not Hamiltonian. Okay? And on the console, this is if G is Hamiltonian, then something. Next, we have if something happens, then the graph is Hamiltonian. And what is this? It is that you have a simple graph with at least 3 vertices, and small delta is greater than or equal to me divided by 2. Okay, which goes along with our intuition that the more edges you have, the easier it is that the graph may be Hamiltonian. Okay, but this is more precise. It's not just on the number of edges, but on the distribution of edges, by saying that something about the minimum degree small delta. Okay, and we have seen one of the few proofs that we have here, and I chose it because it involves that very nice inclusion-exclusion principle, which is one of the most used principles that you have in set theory, but not just in set theory. You have it in very many parts of mathematics. For instance, if you want to judge the dimension of the sum of two vector subspaces, then you have a similar condition, which is Grassmann's equality. Okay, but after that, we have that we can have a rather ugly necessary and sufficient condition. Why do I say that it's ugly? Because it displaces the problem, so to say. First of all, we have to give a definition. Where is it? Here. Oh, yes, here. Closure of a graph. The closure of a graph G is a graph that you obtain by a recursion. This recursion goes like this. You find two non-adjacent vertices whose degree sum is at least the number of vertices you know. Okay? If you find such a pair of non-adjacent vertices, then you join them by an edge. Okay? Now you might have some pairs which were already there before, or you have created new pairs where you have the same thing, that the sum of the degrees is greater than the number of vertices. You put an edge between these two vertices, and so on and so forth. Okay? When you have no more such pairs, you are finished, and the graph which you get is called the closure of the initial graph. Okay? The lemmas I skip because I do not give the proof of what? Of the fact that, here it's not my fault. The ones who scanned this page missed this edge. You should place here an edge, please. It's not on your copies because it's not on the files which are available, but here there is an edge. Okay. And the theorem is this. A simple graph is Hamiltonian if and only if its closure is Hamiltonian. So it's not extremely good because it displaces the problem. You know, sometimes you displace a problem, and the place where the problem has gone is a good place where you can see things. For instance, this is a corollary just after. If you, by building the closure, if you land in a complete graph, then you are done. A complete graph is always Hamiltonian, and so actually this necessary and sufficient condition becomes a good condition. But in general, you would like something like the condition for Euler. I already told you this sort of philosophical way of looking at if and only ifs. Okay? You have something of your interest, but which you can't see. and there is something of no apparent interest, but which you can check, compute, whatever, okay? And if you have if and only if, that's a good thing. And this Euler is very nice thing. You are interested in knowing whether there exist Euler tools, okay? And so you can try, you don't find, but you want to be sure that there exists none, okay? That is what you are interested in, and in the pubs of Königs there, they spent a lot of time and a lot of beer, surely, for trying this thing. Now, on the other side, you have something of apparent no meaning, no interest, but in which you can check directly in a very easy way. You visit every vertex, look at how many edges are incident, and so you can see if the condition is satisfied or not. Even, okay, all are even. The condition is satisfied. The if and only if tells you, okay, that's what you wanted to know. There is another tool. You find a vertex with odd degree, you say, no, don't look for any, don't make your experiments. There is no possibility that you get another tool. That's a wonderful, very simple and wonderful necessary and sufficient condition. This is less good because it gives you the same problem on another graph. It's not something else. It's the same thing that you have to check, but on another graph. You might be lucky that the other graph is easy to see as Hamiltonian, like when the closure is a complete graph, but in general, it's not what you are looking for when you look for a characterization, okay? And this is the corollary. All right, so you can see that the graph in picture 4.7, if you make the closure, you find that it's a complete graph, okay? Here, you build the closure and you see that it's the complete graph, and so you can say that this is Hamiltonian. Why? Because the closure is a complete graph, so the closure is Hamiltonian, and you can say something about this which is rather complicated. For seeing its Hamiltonianness just by look, okay? All right. The graph, okay, that's good. The graph of figure, okay. Figure 4.7 can be obtained from the graph of figure 4.3, but altering just one and one edge. So let's see 4.3. This is 4.3, and just a little difference from here to figure 4.7, but this is not Hamiltonian, while the other one is, okay? And this you can check as non-Hamiltonian just with the counter-positive of this one, okay? Now, let's go to applications of these things. Maybe let's have a look at the closure here. Why is the closure this one with this edge also? Why? Because we have 6 vertices. Can I find a pair of non-adjacent vertices whose degree sum is greater than 6? Yeah. Sorry. Greater than or equal, to 6. Here we have 3, here we have 3, so we have to join. Okay? here we have 4, here we have 2, so we have to join, and this we do. Nothing like that. If you take this plus this, 2 plus 5, we are under 6. Okay, so we are now here. Now you start again. Why? Because here you have 4, and here you have 2, so 4 plus 2 is 6, so you join. This, here you have 2, here you have 4, 4 plus 2 is 6, so you join. Now you get this. Now you start again. And for instance, what about this and this, which so far were not to be joined? Here you have 3, here you have 3, 3 plus 3 is 6, and so you join. And okay, that's all. And then you are here where you have a complete graph, and so surely this is Hamiltonian, but then also the original one is Hamiltonian by this theory. Okay? Of course, here it's extremely easy to see that it's Hamiltonian. Okay? Because it just goes along this cycle. All right? But of course, they show you here an easy graph on which you can easily see that it's Hamiltonian, but just they want to show you the process that you have to do for making the closure. Now let's go to applications. The first one is called the Chinese postman problem, and it's not the problem. Oh, sorry.
Could you please explain the Hamiltonian again, or like very fast? Because the Hamiltonian, how can the graph be a Hamiltonian?
Oh, Hamiltonian for a graph means there exists inside a Hamiltonian cycle, a Hamilton cycle. That means a cycle which touches all vertices exactly once. Okay? If you have that, then you have a Hamiltonian graph. It's easy to see, to produce non-Hamiltonian graphs. For instance, if you have a cut vertex, okay, this surely cannot be a Hamiltonian, because if you are here and you must be here sometimes, then you go through here, and then if you want to go back to this, you have to pass twice through the cut vertex. So it's easy to see that some non-Hamiltonian graphs. Okay, a Hamiltonian one, a complete graph. Okay, but there are quite a lot which are non-Hamiltonian, not being like this, and which are Hamiltonian, not being complete. And you would like to have a characterization, a complete characterization. So far, nobody has one. Okay, and it's I will come back to this problem in a moment. But let's see the Chinese postman problem, which is not the problem of the Chinese postman, but it's the Chinese problem of the postman. Okay, meaning that it was at first considered by a Chinese mathematician. What's the problem? You have, well, for a postman or posthuman, of course, the important objects are streets, are not crossings of the streets, because the postman has to go through all streets to deliver the post. Okay, and so this postman has a border or part of the town on which to deliver post. The ideal thing, of course, would be that this postman goes through each that he or she has an Euler tour, of course, so that there is no going twice through the same street. I've gone through this street, I have delivered the post on this street, then I go somewhere else, I prefer, if I have not to go through the same street without working, without delivering, okay? And so, the optimal thing would be to have an Euler tour. And all Euler tours would be equivalent. But since it's difficult that actually your part of the town is Eulerian as a graph, then what the postman would like to do? Again, we have weights, meaning in this case lengths on each edge, and so you would like to minimize your journey. Okay. If the graph is Eulerian, however you do a Eulerian tour is all right. It will have total the total sum, the sum of all lengths of all edges. Okay. If not, you are bound to go at least twice through some streets. Okay, and you would like that these streets which you go through twice are totally of minimal length. Do you follow me? That's reasonable, isn't it? And so you have this problem, which is again an optimization problem, which is something which comes very often with graphs, to find optimal something. Okay, we have seen optimal connections from a particular vertex. Now we see the problem of optimal trail, optimal close trail, because the postman goes back to the initial point. Okay, in the sense that if you have to go twice through some streets, then you would like to do it with minimal double length. Okay, and so there is a way to do that, which is called Fleury's algorithm. Okay, which constructs an Euler tour, and the algorithm is this. Choose an arbitrary vertex, okay, and you put that vertex as V0. Then choose, now suppose that you have already taken in some edges, some vertices, and edges V0, E1, V1, and so on, up to EI and VI. Then you have to choose a further edge EI plus 1, okay, out of the remaining edges, okay? And what are the rules? That this edge is incident with the last vertex you have chosen. You are building a trail, okay? And so you must continue your trail, your walk. You must continue from the vertex you have reached so far. So you have reached VI. You must consider an edge which has VI as an end. And unless there is no alternative, the edge you choose must not be a cut-edge of what? Of the graph that you obtain by deleting the edges already taken. Okay? And, okay. But you might be in the condition that it's a cut edge anyway, and if it is the only possibility for an edge starting from VI, then you still take it. And then you stop when step 2 can no longer be implemented. Okay? And what you get is trailing. Okay? I suggest that we use it, okay, for seeing how it works on one of the graphs which were given as an exercise. Okay. For instance, I would take this without this one, without this edge. Why this? Because it can have, it has surely an Euler trail with the origin and terminus, these two vertices which have degree 3. Okay, so if I get rid of this edge, this vertex also has degree, even degree, and so we can try that. So let's say A, B, C, D, E, F, G, H, M, N. Okay? I know that I have to start either from here or from here. Let me repeat here all these, and then I will delete one by one the edges I take in. Okay, let's start from here, for instance, and okay, I just write down the edges and the names for, okay, actually you can also put names for the vertices. Okay, A, B, C, D, E, and F, and so we have to see the capital letters. Okay, so I start from A. I start from A, and I take any edge which starts from A. I have not yet taken any edge, so if I don't have to check that thing of deleting the preceding edges. I have no preceding edges. So I can choose whatever I want. C, for instance. So A, small c, and I land in B. Okay? So, okay. Now here I delete C. Okay? And now I look, what can I take? I can take either M or D. None of the two is a cut edge of the graph we are left when we delete this. What do you prefer? D. Okay. So I take now D and land in capital C. And here I delete D. Okay? I am in C. I can choose E, F, or H. F or right. F is not a cut edge of what we have here. So F, small f, and we land in E. But here I have to delete small f. Okay? Now we are in E, and we can take A, G, or B. None of these is a cut edge. Okay? So, G, all right. Let's take small g. So I land in capital F. And here I delete edge G. Okay, now I'm in capital F. I can consider either M or H, but what happens? M is a cut edge. But I have an alternative, H, so I must take H and not M. Okay? So, is it clear? Okay. So small h and I land in C. Now I delete.
Why did you take the M?
Because it is a cut edge.
No, not M.
Oh, sure. Sorry. Also N was possible, of course. Sorry. Okay. But eventually we would take it anyway. So we take H. Yes, it was anyway possible. Okay. Okay. So we are in C now, and so I've deleted a small h, and now I have no alternative. This is a cut edge, but it's the only one now incident in C, so I must take it anyway. Okay? E, and I land in D. And I delete, and now I'm in D, but we're in the same situation. This is a cut edge, but it's the only one I can use. So I take small a and land in E. And now again, I only cut edge, but it's the only possibility, and so I take it. And so B, and I land in A. And I delete also B. And again, I have just a cut edge, but I must take it. And I land in F. And finally, same thing, I delete M, and I must take F. So, if I have an Euler trail, I complete the Euler trail. If I was so wise to start from a vertex of odd degree, otherwise I cannot. Okay, and if I have an Euler tour, I complete the Euler tour by Fleury's algorithm. Tell me.
By this one, you are going to reduce the roots, or what is the? Why are we doing this?
What's my task? What was my task?
Yeah.
It was to solve the problem of going from one vertex to another vertex by what would the yes, by not if I follow this, I do not have to take the chalk out of the blackboard. So A, C, D, F, G, H, E, A, B, and M. Okay, I do it. What the problem was, it was actually impossible because of that small edge which I took away here. But it was. Can you draw that without taking your pen away from out of the paper and without going twice on the same line? So never. Pardon me?
Vertex is important for edges are important.
Here it's Euler. No, I must go through every edge exactly once. Euler. Every edge exactly once.
The vertex are important.
No, sorry. This is connected to the first part of the chapter. Euler. Okay? Now we go to a similar problem, but for vertices. And it's called, a very well-known problem in optimization, which is the traveling salesman problem. Meaning that again, like the initial situation is the same of the postman, meaning that you have streets with length and you have streets with lengths and you have to minimize your journey, the length of your journey. But the task is different because this time you are not interested in streets, you are interested in vertices. You are a traveling salesman and you must visit all towns of your domain, okay? And of course, you would like not to go twice through the same town, so you want to come back home, and so you would like to have a Hamilton cycle. Not only, but mind, if your graph is Eulerian, all Euler or possible Euler tours have the same length, which is the sum of all lengths. Okay. Here you have seen that we had. You say, why not n? We could have chosen n at that time. The Euler train would have been different. Okay, but still you are going through the same all edges, and so at the end you have gone the same number of kilometers. Okay. But if you are not caring about edges, but caring about visiting only once, if possible, your towns, okay, you have choice of different edges of different streets, okay? And so you might have that you touch all towns, but you make a long journey, or you touch all towns, but your journey is shorter. And so the problem is minimize the total length of the journey by touching all towns. At least once, of course, it's better if only once. Okay? But the general problem is touch all towns, at least every town, at least once, and minimize your total journey. Sometimes you are necessarily bound to go twice through the same vertex. We have seen that, for instance, if you have a cut vertex, if you have a pendant edge, so a town which is at the end of the only street going there, or something like that, okay? And so it's possible that you are bound to go through the same town twice, or more than twice, but anyway, the problem is there, minimize your total length. This is very important, and if you're interested in this type of problems, you might know that there is a $1 million for something like that. Why? Because there is the problem of computational complexity. I think we have already talked about computational complexity. It is well, you have a problem which has a size, okay? you have, typically you have to put in order n numbers, okay? How many operations does your algorithm employ for solving the problem? That number of operations is a function of n, of the number of objects that you have to put in order. Are you with me? Of course, if you have to put three numbers, to order three numbers according to their size, you have few operations to do. If you have 10 numbers, you have more operations. But you can find what the number is according to the size n of the problem. Okay, so you have a function of the size n. How is this function? The optimal thing is that it is polynomial and polynomial of low degree. Okay, so you are rather happy if it is order of n square, very happy if it's order of n, so linear in n, and it is absolutely impracticable if it's not polynomial, and it is with what is called combinatorial explosion or combinatorial curse. Even, okay, which is you might need to use factorial n, for instance. If your complexity is the type factorial n, then your program is the worst possible program, okay? Because very soon it will take years for solving a problem of even not big size, okay? Do you see what I mean? So the considerations on computational complexity are very important, for instance, for what concerns the cryptography. Public key cryptography. Have you ever heard about this? Have you ever heard this expression? Somebody has never heard cryptography, public key cryptography? No, everybody has. You didn't? No. It's what you use without realizing. If you go to HTTPS, okay, so you eBay, Amazon, you want to buy something, and you must send your credit card number. That's a delicate thing to send in the net, because it has many places to go through, and in between there might be the bad guy who captures your number and uses it, okay? And so you want to send it encrypted, meaning with a code which cannot be decoded by somebody. The interesting thing is how went these things or codes up to not so many years ago. I wanted to send you a message encrypted, so we have to meet personally. I give you the key, which means, I don't know, letters corresponding to numbers, okay? So I give you my table, it's a lookup table, and so when you see 3, you know that it's U. When you see 4, you know that it's M, and so on. Okay, so I give you something written in numbers, and with the lookup table, which I've given you personally, you can decode it, okay? How can you do that if I am the bank and you are one of the millions customers? I am Amazon, and you are one of the millions customers. We cannot go and meet, okay? So the idea is that you, not you personally, but your computer, has a public key for encrypting. This is strange, because you think if the key for encrypting is public, then you can use the same key for decrypting. But it's not like that, because of an old theorem in modular algebra. Again, the Chinese are in that it's called the Chinese theorem of the remainder. and by a theorem which was discovered when nobody could even think of a computer and so of the internet or anything. Then through that theorem, it's possible to have a key by which you can encrypt, but nobody can decrypt apart from me. Why? Because I have built that key in a certain way, and so I know something, which is in the most common case, I have a key which is the product of two very big prime numbers. I know the prime numbers, the two factors, but you and the bad girl who tries to pick up your credit card number, she knows the number, the product, but she does not know the two factors. But everybody can find the two factors. Only the fact is that it would take hundreds of years to find them. Okay? So this problem of complexity is of extreme importance in today's technology. All right? So it's important to evaluate complexity of algorithms. And what we have is that there is a bunch of problems apparently very different from each other, but whose solution is the solution of another, and the solution of all of them are connected, which are called NP problems. What are they? They are problems for which no known algorithm of polynomial complexity is known so far. Only factorial complexity for them is known, but it's maybe because we are silly, we are not good, and maybe it's a matter of some genius or of some years, and somebody comes out with an algorithm of polynomial complexity. Okay? They are of not for the moment, not polynomial complexity for finding a solution, but of polynomial complexity for checking a solution. Can you see the difference between these two things? Meaning, for instance, I give you a graph. Is there a Hamilton cycle? Maybe it's big, I don't know. I say it is, there is a Hamilton cycle, and I show you the Hamilton cycle. You just have to go along the cycle and see that it touches all the vertices once. So checking is something which you do in, so to say, linear time. Finding, no. Okay, so there is this difference of finding a solution and checking that the solution is actually such a solution. Okay, and this bunch of mutually related problems is called NP, and there is $1 million for the solution of finding that one, and so all of them are actually solvable in polynomial time. So the person,
Have you tried to solve it?
I have no idea. It's
You cannot, so we can also.
there are quite a lot of people doing that, but the cost is not $1 million. It's billion dollars. Why? Because all these public key cryptography systems are based on the fact that the complexity is difficult. Okay, and so if somebody finds a quick for our way of thinking of it, polynomial complexity, an algorithm solving the same problem with the polynomial complexity, not only that person wins the $1 million, but immediately you have a cataclysm in the net. Because immediately all the transactions are not safe anymore. Can you see? And there is a big danger like this in this moment. Maybe you have heard that the quantum computer of Google has reached something. Okay. One possibility for bypassing the problems that I'm talking about is quantum computing. And actually, for a very artificial problem, a sort of a problem exactly made for that check but of no use in general, has been solved in 200 seconds by the quantum computer of Google, while the most powerful classical computer, which is an IBM, would have taken 10,000 years. Okay, and so you see that there is a little problem about that. If you use the normal algorithms, the normal computer, it's something. A way of bypassing the thing, which would not give you the $1 million of Clay's Institute, but which would give you all transactions of Amazon and eBay and every bank and so, would be through quantum computing. Okay? And so, this thing of the traveling salesman is very important because it was the first to be recognized as an NP problem, and it is the paradigm of these problems. So all are related to this particular problem. All right, and also knowing whether a graph is Hamiltonian or not is again an NP problem. Okay, so a very big difference from this type of problems related to Hamilton and so vertices, and a very similar problem related to Euler, so to edges. And you can see how going from edges to vertices can change radically the type of study and the results. Okay. Any questions? Okay, so let's say 10 minutes break and then we change chapter. Okay? 7 past now, and so 17 past I start again.
Just a moment today.